Okay, let's get started. We don't have many lectures left, but we have a lot of fun material. So we're going to continue interconnects. That's going to be a lot of fun, I think. I'm going to give you a glimpse of some of the research in this area today, although we're going to first finish some of the fundamentals that we didn't cover yesterday. Can people see the screen? That's good, right? Okay, so this is what we covered mostly yesterday. Essentially, we talked about three major things in an interconnect: topology, routing, and buffering and flow control. And we talked about a lot of topologies, the way switches are wired, and we said that this affects pretty much everything that you design in a network. We talked about routing, different ways of doing it, and buffering and flow control. We were discussing like what to store within the network, how to handle things when things are oversubscribed, how to control the flow of packets in the network. And we said that this is tightly coupled with the routing strategy, right? Actually, all of these are coupled in some way, but some are more coupled than others, as we will see later. And we ended up discussing a modern virtual channel-based router, right? You have input ports, you have output ports, and essentially we talked about head-of-line blocking. As a result, we had not a single FIFO, first in, first out queue over here, but multiple FIFO queues. And when you have an input channel, you go into one of these FIFO queues, and then there's arbitration that happens for a given output port. All of the input ports and the FIFO queues within each input port arbitrate, and somebody wins the arbitration. So there's a lot of complexity actually in a router. That's one of the reasons why people don't want to examine all of the potential headers that exist in the router itself. That's why they build things with FIFO queues in general. So I like thinking about this in comparison to an out-of-order processor. In an out-of-order processor, you have an instruction scheduler also, right? And that instruction scheduler, no, there's some sound coming. And that instruction scheduler essentially looks at a queue, and it basically tries to pick the instructions that are ready to schedule, right, to some functional unit. Functional units could be output ports over here, right? It's essentially a very similar problem. You just need to make sure the dependencies of the instructions are satisfied whenever you wake them up. But if you look at an out-of-order processor, it looks at a window of instructions. It can basically pick the instruction from any point in the queue. So it's really this window. It's not a FIFO queue. It's really an out-of-order scheduling window. You could do the same thing over here, actually. You could basically have a single huge buffer, a single buffer over here, and basically pick the oldest packet that wants to take an output port by searching the entire buffer, right? That's certainly possible. But people usually don't do it today because of the complexity associated with it. And historically, it hasn't moved that way, I guess. Historically, processors have been much more aggressive in terms of how they pick the instructions to schedule to functional units, as opposed to routers in terms of how they pick the packets to schedule to output channels. Yeah, that was. But it's good to think about these things as being very similar, in my opinion. But the designs in the end up being very different. Because if you think about it, in an out-of-order processor, you need to have something like this also, right? You need to have this sort of network to distribute an instruction from a particular place that you fetched it from into the corresponding functional unit that it wants to go to. And the functional units could be heterogeneous because you don't necessarily go to every functional unit. An add doesn't go to a divide functional unit, for example. Okay, so this is really nothing new in that sense, but it's new in the sense that the way it's built is a little bit different. So you have routing logic, clearly. Do you hear that sound? Do you know why it's happening? That's the harder question. I don't know why it's happening, because it didn't happen before. I'm going to reduce the volume a little bit more and see if that fixes the problem. Okay, let's see. Okay, so basically you need to allocate all these resources. You need to allocate the virtual channels whenever you actually want to receive a packet. You need to allocate an output channel because you can actually, depending on the routing algorithm, you need to compute the route for all of the head flits inside here. So there's a lot that goes on in a router. And if you have buffers, there's a lot of allocation that you need to do. And you need to make sure it's correct. And you also need to allocate who goes into the switch, for example. Existing routers are actually very speculative. They try to minimize the amount of time they spend. For example, they overlap some of these different tasks. Essentially, you don't want to waste cycles in terms of deciding which packet to schedule next. So that decision process, they perform a lot of speculation. They basically do speculative allocation of the switch. They sometimes do speculative allocation of the virtual channels. So there's a lot of speculation that's built into a very high performance router today, which I'm not going to go into. If you go into it, it's going to be a lot, but I'd be happy to point you to papers. Some of the papers that I've discussed actually go into more detail in terms of how this really operates. Okay, so we were talking about virtual channels. I covered the slide relatively quickly. Essentially, virtual channels are there to reduce head-of-line blocking. Because you have a single queue, you may have head-of-line blocking, even though a packet wants to go to a particular output channel, and the output channel is free, it cannot go because you don't even consider that packet because you have a FIFO queue. Now, if you have multiple smaller FIFO queues, you reduce that head-of-line blocking. But virtual channels enable other things also, like deadlock avoidance. You can basically switch to a different set of virtual channels on some turns, and basically break the cyclic dependency of resources. Depending on which turn you're taking, you can go to a different virtual channel. Essentially, virtual channels give you another network, if you will, because if you go through some virtual channels and have different routing algorithms for different virtual channels, you can actually have a deadlock-free routing algorithm overall. Yeah, you can enforce order on the virtual channels. You can have escape virtual channels, as we've discussed, have at least one virtual channel that uses deadlock-free routing. And we discussed protocol-level deadlock yesterday. I'm not going to go through that again. But we will see an example of protocol-level deadlock later on when we talk about bufferless networks. So all of these are very fundamental. These exist. Some of these things, like protocol-level deadlock, exist in bufferless networks. We will see that. And virtual channels enable prioritization of different traffic classes. Now you can assign higher priority to some virtual channels for whatever reason, right? If you want to provide higher quality of service to some flow, basically you direct that flow to that particular virtual channel. And okay, this was the review that we ended up with yesterday. Essentially, this was a store and forward network. It was high latency, high buffer requirements, because you have to store the entire packet and then forward it. That's why it's called store and forward. If you want to get rid of a lot of buffering and reduce latency, you go through a virtual cut-through or wormhole routing, where essentially head, body, and tail flits are distributed across different routers, and you store only flits. You don't store the entire packet in a router. And then we said that this has head-of-line blocking issues, which we demonstrated with this picture. This red packet cannot move, even though this channel is free. It cannot move because somebody else cannot get scheduled to some other output port, which is pretty stupid, actually. If you design this sort of network, you don't want to do that. So having multiple FIFOs actually gets rid of that. Now this red packet can move. Okay, so there's a lot of complexity involved, and we built essentially almost a state-of-the-art router with the picture that I've shown you. One thing that we didn't discuss is you need to communicate whether a buffer is available or not, right? If you actually want to allocate, if you want to send a packet to a downstream router, you should know whether a buffer is available. If not, then you may have a problem, right? Especially if you have, if you're relying on buffer availability. So these are the different flow control methods that are used to communicate buffer availability upstream. Credit-based, on and off, ACK or NACK. So essentially, credit-based flow control says upstream routers know how many buffers are available downstream. The downstream routers that are receiving the packets pass back credits to the upstream saying, I have this many buffers available. And this leads to a lot of signaling between the routers. So there needs to be another network that carries these credits just to ensure that buffering is done correctly. So it's a lot of overhead, as you can see. We will see an example of this in a little bit. On and off, and also there's delay, right? Of course, you may be sending a lot of packets downstream, but other people may be sending a lot packets to the same router, and the router needs to be conservative because it may actually receive packets from different routers at the same time. So it needs to be conservative in communicating how many buffers it actually has, right? it cannot tell you that it has a lot of buffers and then it runs out of buffers. So there's some delay associated with this credit communication, as well as there are multiple different routers communicating with the same router, so that needs to be taken into account. As a result, your buffering becomes more conservative. You need to over-provision your buffers, or you run out of buffers more quickly. You basically quickly say, oh, I don't have buffers, right? So there's a danger here. That's why a lot of the buffering is over-provisioned in high-performance networks today. So the on and off flow control is a different method. It basically says, stop sending me messages, packets, because I don't have buffers, or now you can start sending me packets. It's on and off, basically. It's different from how many buffers I have. I have credits or not. ACNAC is essentially, ACNAC means upstream buffer upstream router optimistically sends the packet to downstream router, but it cannot deallocate the buffer until it receives an ACK or NAC. Right. But of course, this may have downsides like inefficient utilization of buffer space. But they all have downsides in the end. Okay, let's take a look at credit-based flow control. You have node 1 and node 2 over here. Let's assume that node 2, at some point, a flit leaves the router. Now you have one buffer available. And at time t1, node 2 sends a credit to node 1. Of course, in this case, it's just node 2 and node 1, right? What if you have node 2 and node 1, node 3, node 4, node 5 that can potentially send to node 2? So you need to send credits to all of them. The question is, how much credit do you need to send? So if you have only one buffer, you cannot tell everyone that you have one buffer, because now everyone will send you will receive 3 packets in the next cycle. You cannot do that. So you need to over-provision your buffers, or you need to be very conservative when you're sending credits. Either way, either you reduce your energy efficiency because you have a lot of buffering or area cost, or you basically do not utilize your network very well because you tell everyone, I don't have buffers, even though they may not be sending you anything, right? Okay, so you also see that there's a delay associated with this credit round trip. So this node basically will think for some time that it doesn't have a credit. There's also that round trip delay. So it processes that credit and it sends a flit to the next node. And once it sends a flit, it has one buffer available, so it passes the credit back to upstream routers. Again, the same issue exists over here. And then once this node gets the flit, it processes it, and there is a round trip delay associated with even a single flit sending, as you can see over here. Basically, we have a flit, you need to wait for a credit, and then you send the flit, and then only after that it takes some time to fill the buffer, as you can see over here. So from here to here, your buffer is really empty, if you will, for all practical purposes. So you're underutilizing this buffer because of this credit round trip delay. Plus, on top of that, this is just one node and 2 nodes communicating. So you need to over-provision your buffers. This is why buffering becomes a little bit unwieldy if you want to have high performance. Okay, basically the time between when the buffer empties and when next flit can be processed from that buffer entry, that's credit round trip delay or round trip credit delay. This leads to significant throughput degradation if there are few buffers available. That's why the high performance network over-provision their buffers. And of course, it's important to size the buffers to tolerate this credit turnaround. This is also called turnaround delays. Okay. So let's take a look at another example of this buffering. This is on-off flow control. Again, we have node 1 and node 2. Downstream router node 2 has an on-off signal to upstream to tell the upstream, you can send the buffer, you can send me the flit right now. So node 1 sends a flit, and there, because of that flit received by node 2, the off threshold gets reached. And node 2 tells, okay, I don't have any buffers anymore, so stop sending me. Of course, you need to be careful here. You need to send the signal, again, conservatively, because if you send it too late, again, a lot of nodes may send you flits and you may not have buffers, right? You need to basically turn off yourself conservatively. And as you can see, that's the conservatism, right? So flits may be still being received over here. So there's some slack that you need to build into this off signal. This off signal assumes that, oh, I'm going to receive some more flits. That's why I'm going to send the off signal even earlier. Okay, so there's some processing delay, and then, basically this off threshold is set to prevent flits arriving before T4 from overflowing. Yeah, basically that's not written very well, but basically you need to ensure that the buffers in node 2 do not overflow. So you need to turn off, set that signal at the right time. Which means that you need to over-provision your buffers again, right? Or you don't utilize your buffers really well. Okay, and then once node 2 starts sending flits, after some point, you turn on, basically you have enough buffers in this node, and then you can now turn it back on and send an on signal back to any upstream router. Okay, basically it goes on like this. And then now you can keep sending flits, and that processes, and then this can keep receiving flits. Okay, makes sense, right? And this on and off signals are set such that you never overflow these buffers. And as a result, you have conservatism, and your buffers become large. So buffer management is not easy. Basically, that's the whole point over here. And you have a lot of buffers. Especially in complex topologies, this becomes not easy. In a mesh, you really have 4 places where you can receive flits from. Actually 5 places, right? The input node and northeast southwest routers. I've just shown you one. You need to actually manage all of these on-off signals for all of them. Okay, I didn't look at ACNAC, but ACNAC actually has similar problems. Okay, so we'll get back to buffering. Let's talk about evaluating interconnection network performance now that we're done with the real basics. Performance is also basics, and I've given you this figure before, right? We talked about load latency curve. This is essentially the load latency curve. Usually if you want to look at an interconnect, you think of it this way. There's some injection rate to the interconnect, and that injection rate can be expressed in different ways. One way of expressing it could be how many flits per node per cycle are being injected, right? And you can have a number based on a workload or based on some particular synthetic pattern, as we've discussed last time, like a uniform random pattern. And that can go from, I guess, 0 to whatever. There's another way of expressing this, basically. It's also called how loaded the system is. It's fraction of the total buffer space and the link space that is utilized. And there's a percentage over here, like maybe 60% of all of the buffer space is utilized. You can also express the load of the network that way, and you may see that in some works. But basically this says how frequently are you injecting into the network. On the y-axis you have the latency. That could be average packet latency or maximum packet latency. Let's talk about average packet latency. And then you have a curve that looks like this usually. Essentially you have some point where you're not injecting anything. You have some latency that's minimal, right? That's called zero load latency. Of course, if you're not injecting anything, how do you measure something? You don't. Basically, this is assuming that some traffic pattern, if the network is not loaded, how long will it take for the packet to go from a source to a destination, right? That's what zero load latency means. And if you keep increasing the load, your latency increases because there's contention. And at some point, what happens is network essentially saturates. So this asymptote over here is called saturation throughput. And at that point, your latency shoots up. Sometimes it's called also congestion collapse in the internet, for example. Basically, the network collapses because of congestion. The latencies become too unreasonable at some point. So that's the saturation throughput of the network given a traffic pattern. So this curve is not the same for every traffic pattern, clearly, right? If the traffic pattern is uniform random, meaning any node can communicate with any node in a uniform random manner, that's very different traffic pattern compared to nearest neighbor. Nearest neighbor means a node is communicating only with its left neighbor, let's say, or right neighbor. That is not putting a lot of strain on the network, buffers, links, whatever you have, which means that the curve for nearest neighbor probably looks like this. Right? It saturates very, very late, if it saturates at all. At some point it saturates because you run out of links and buffers, right? But the curve for uniform random looks more closer to here, basically. It saturates much more quickly because every node is sending packets uniformly randomly to every other node. That's clearly putting a lot more strain on the entire network's resources compared to nearest neighbor traffic. So there are a bunch of different traffic patterns that people analyze usually. Of course, real patterns are somewhere in between probably, right? Okay, so let's take a look at how the fundamentals that we've discussed affect this curve. Because if you think about it, this curve, assuming the traffic pattern, let's pick uniform random. Uniform random is interesting because it basically makes every node equal, and there's no predictable communication pattern in the network. You can think of it as a worst case pattern. It's not really a worst case pattern actually. It just basically is a load balancing pattern. One of the worst case patterns could be a hotspot pattern, right? Hotspot is you have actually, let's say you have a mesh, you have one node that's a hotspot and everybody's sending messages to that node. That saturates the network actually much earlier than uniform random in general. So you see a curve that looks like this very quickly. And if everybody's sending, injecting into the network at a very high rate to that particular hotspot, things get actually congested much, much worse. That's why your routing algorithm is very important, especially with those hotspot patterns. Okay, so let's assume one particular injection pattern, workload pattern. How is this curve, what determines this curve? Basically, there's some minimum latency that's really given by your topology. You cannot go beyond that, right? Your minimum latency, this is actually your diameter, especially your topology's diameter. If your diameter is low, your minimum latency is usually low. If your diameter is high, your minimum latency is high. So topology is very fundamental, as you can see. And on top of that, there is some inefficiency because of your routing algorithm, because you don't necessarily do a good job in routing. Or there's some latency in routing, fundamentally, that affects your minimum latency. So routing algorithm affects that. And on top of that, there's flow control mechanisms, just like we've discussed. All of the buffering overheads, essentially buffering overheads or the management overheads of the flow that adds to your minimum latency. As a result, you get to this point. So topology, routing algorithm, and flow control all together get you to a point over here. Okay, so that's your zero load latency over here. So let's take a look at throughput. Throughput is also, again, bounded by topology over here. Topology bounds your throughput. You cannot go beyond some throughput if your topology is not good enough. And on top of that, you have some inefficiency in your routing because your routing algorithm is not perfect. There's some delay, and it's not high throughput perhaps. And then you lose some throughput because of that. And then on top of that, you lose some throughput because of your flow control mechanisms. And as a result, you reach this asymptote over here. So you're bounded by two asymptotes, the latency asymptote and the throughput asymptote. And they're all affected by, firstly, your topology, and then your routing algorithm, and then your flow control mechanisms. It's good to think about that. Of course, it's hard to exactly figure out what contributes how much to it, and that's part of the design of the network, basically. You want to design a network based on your requirements that minimize these inefficiencies as much as possible. Okay, so I've already said that this is the zero load latency, and that's the saturation throughput. Okay, so basically, a ring topology is very different from a mesh topology, if you think about it. Minimum latency of a ring is much larger for a uniform random traffic pattern compared to a mesh. And we've discussed that. And definitely a point-to-point network is, its minimum latency is much lower, right? Its diameter is 1. And there's no switches that are involved in that transmission. Okay, so ideal latency, we'll go through this very quickly basically, but this is solely due to the wire delay between the source and destination. Usually you want to approximate ideal latency, and point to point is getting very close to that, right? You have only a wire between a source and destination, hopefully. But even there's some arbitration delay, actually, because you need to figure out which wire to put your message into, right? Because you have many, many wires connecting yourself to many other routers, many other destinations. But this is the ideal latency. There's some distance, the distance between 2 points measured along axes at right angles, Manhattan distance. And then there's some propagation velocity of the signal, and you have that d divided by v, and also you have some packets, right? You have a packet size and channel bandwidth, and you basically put some number of flits. So that's the ideal latency, and you can study it. It's not that interesting in the end. But on top of ideal latency, you have overheads. Actual latency is, you don't have dedicated wires only, but you actually have router latency. So there's additional router latency and the number of hops that you need to travel, plus latency due to contention. And this router latency can be broken down into more but I'm not going to do that. It's not just the routing latency, but it's also the credit round-trip flow control latency. So there's a lot that goes into the router latency also. And certainly the latency due to contention is not so easy also because it depends on the contention patterns, right? Okay, so this is what a latency and throughput curve looks like. This doesn't have to be on-chip network, but this slide happened to be on-chip network. But basically this is the fraction of the capacity of the network that is occupied, injected, and this is latency, and the curve looks like this usually. And the ideal, you would like this perhaps, right? Maybe this is your really minimum latency. Of course, you could argue that ideal should be much closer to here, but ideally you shouldn't saturate, right? But you do saturate because your network is not ideal. Okay. Any questions so far? Okay, let's look at some network performance metrics. We've talked about packet latency. Round-trip latency could be another one. And packet latency could be average and maximum. Round-trip latency is not just packet latency, but request-response latency. You send a request and you get a response. What is the round-trip delay for that? And saturation throughput we also talked about. So these are actually very traditional performance metrics that people use, and you can actually gather them from here. But I think actually a lot of works, especially in on-chip networks, more recently I focused on application level performance, system performance, and this is really important, as you know by now. This is affected by interference among threads and applications also. So this is really important to consider. So we'll take a more application level view. And if you actually think about the applications, maybe there's a different way of designing networks. In the past, people actually thought about traffic patterns and looked at traffic patterns and the network's performance based on those traffic patterns. That's good, interesting, but you don't know whether those traffic patterns are actually going to be the real patterns that are going to be used in your network. If you look at an on-chip network, actually there are real workloads that are running on that network, and you can actually design your network to the requirements of those workloads. So that brings us to on-chip networks. Let's talk about on-chip a little bit. Everything we've discussed is much more general, actually. Actually, what we're going to discuss is also much more general than on-chip, but I'm going to motivate it based on on-chip because it's as I said, today's systems are actually distributed systems on chip. So if you look at on-chip networks, these are networks that today connect cores, caches, memory controllers, and other components, accelerators. And buses and crossbars are some types of networks, but usually they're not scalable. So people have been looking at things like rings, hierarchical rings, and meshes, or tori. But you can think of it this way. You have routers and you have processing elements, and processing elements can contain cores, banks, memory controllers, etc., or accelerators. Usually they're packet switched, but you could have circuit switching mechanisms. And two-dimensional mesh has been most commonly used topology in especially the scalable prototypes. This doesn't mean it's not necessarily a good topology. It's easy to do, right? It's easy to lay out. And you can imagine why. It looks like this. It's very regular. You basically stamp out a bunch of tiles. But one thing that's fundamental is the on-chip network primarily serves cache misses and memory requests. So if you look at these processing elements, they usually have L1 caches internally. So they have some locality that's already filtered, and those L1 caches do not communicate. Only the cache misses get served over here, and the memory requests get served over here, and some coherence requests, of course. But if you have the MESI protocol, if you're modifying your data exclusively, you know that nobody else has the data, so you don't actually need to send a coherence message to anybody else, right? Once you have exclusive access to the data that you're modifying, you don't need to keep it coherent. Okay. So certainly there's coherence request over here that should be added. So this is another picture over here, and this is the router that we've seen. And it's very similar to what I showed you earlier. So let's talk about on-chip versus off-chip a little bit. There are on-chip advantages to on-chip, and there are disadvantages to on-chip also. Clearly, if you're on-chip, your latencies are much lower compared to off-chip interconnects. Off-chip interconnects are huge, and you have to go off-chip. So latency is a big difference. There are no ping constraints. So that's actually a big difference between on-chip interconnects and off-chip interconnects. You're not going off-chip, as a result, no ping constraints. So your routers can be much more complicated, potentially. They're rich wiring resources compared to off-chip again. If you think about off-chip, you have real big wires, but these are also real wires, but they're, you can even think of them as small, nanowires, right? People are actually working on even smaller wires. So as a result, you have very high bandwidth on chip, and you may have simpler coordination because you're restricted to on-chip, right? Of course, on-chip has constraints and disadvantages. Off-chip, you don't have a two-dimensional substrate, but on-chip, you're limited by the two-dimensional substrate, right? So you need to lay out on this two-dimensional substrate, and as a result, you're limited by your wiring resources, and your implementable topologies get limited. How many metal layers, for example, you have limit your implementable topologies. And energy and power consumption is a key concern on chip because you're limited. The limited power is true everywhere, but on chip you may actually have even more constraints because you have things that are consuming that power, like processing elements. So complex algorithms are usually undesirable because what you put over here is really hardware-based algorithms, and in hardware you don't want complex algorithms in general. Whereas if you have a router that's doing software-based switching, the algorithms may not be that hard to make complex. And also you have logic area that constrains the use of wiring resources. You may have a lot of wiring resources, but you don't want to have huge area in your router, for example. Okay, so let's take a look at cost, channel characteristics, and workloads. If you look at cost in off-chip, cost of the network is dominated by channels, pins, connectors, and cables. Whereas on chip, a lot of these are cheap, but storage and routers are not that cheap. So basically, your cost is really dominated by your buffering and switches. Whereas if you look at off-chip, your cost is dominated by some other things that are much bigger. So as a result, you have networks with many white channels and fewer buffers, and we want to get rid of even more buffers on chip. So if you look at channel characteristics, on chip the distance is short, you get low latency, and you have you need repeaters every whatever millimeters, so that you can actually satisfy the clock rates that are on chip. And you can also put logic and repeaters. And workloads, as we discussed, on chip you have multi-core cache traffic, but if you look at off-chip networks, it's more like supercomputer interconnect traffic, which could be very different from the traffic that you have in a cache-coherent multi-core system, right? And if you think about the internet, actually, it's a different type of traffic than even this one, right? It's very different. The characteristics that you have are very different from multi-core cache traffic. So it doesn't make sense to actually design networks that are similar on chip versus off chip. You really want to adapt to the characteristics of these different constraints. And if you're interested more in this, we've actually written a paper that was published in SIGCOMM in 2012 that talks about on-chip networks and off-chip networks and their differences, and looking at congestion and scalability in multi-core interconnects. As far as I know, this is the only paper that was ever written in SIGCOMM on chip networks. SIGCOMM tends to be a very closed community in general. They don't like different things somehow. But it's very interesting, I think, to think about those differences between on-chip versus off-chip. Because if you think about the history of how networks have evolved, a lot of networks that went into on-chip, at least a lot of networks that were designed in academia, people were thinking, oh, let's do similar things that we've done off-chip. But it's not a good idea, I think, in general. Whenever you have constraints that change, you should really rethink how you do things. So I think this paper is an example of that rethinking. And I'll give you some more examples of that rethinking. And that starts with buffers, I think. So if you think about off-chip, buffering is maybe good, but we've discussed a lot of the downsides of buffering also. You need to manage the buffers. But buffers are actually good because they're good for network throughput. So this is the load latency curve. And if you assume some sort of traffic, let's say uniform random, if you have a lot of buffers in your network, the curve is to the right over here. Your saturation throughput is high. If you have a very small number of buffers, the curve is to the left over here. Your saturation throughput is low. And this makes sense because if you don't have enough buffers, you cannot keep injecting into the network, right? It's fundamentally, it's a fundamental characteristic. You keep injecting into the network, but there's nowhere to inject to. So your network saturates. So this is what you get with buffers. So that's a big advantage of large amounts of buffering. Of course, it has other advantages. You can handle congestion better potentially. That's true, but it's not depicted over here. It's depicted in the sense that it affects the average packet latency and saturation throughput. Actually, the curve over here is not shown very well, I think. We didn't look at this part very well, but if you have small buffers, your packet latency may be lower, actually. So the curve actually may look like this. Small buffers, your minimum packet latency may be lower because you don't need to manage a large number of buffers, right? Okay, so this is the good part. But there is a bad part also because buffers consume significant energy and power. They consume dynamic energy when you read and write. And they consume static energy even when the buffers are not occupied. Right? This is essentially buffer. And the technology you use to design buffers matters a lot. If you use an SRAM technology, then your static energy is lower. But if you use like register file technology, your static energy is even higher. So of course it depends. It's not easy to use DRAM technology in these buffers because it's not very low latency, right? And buffers also add complexity and latency because you need to have logic for buffer management, and we've seen that. Virtual channel allocation, credit-based flow control, and this actually complicates the network quite a bit. A lot of the complications that we've discussed is because of buffering. Certainly routing itself has complication, but buffering adds significant flow control. You actually need a back network to handle these credits, ACK-NACs, or on and off control, right? And also they require significant chip area. There are a bunch of prototypes that show that the buffers occupy a significant fraction of the total on-chip network area. 75% is probably a very high number. Maybe these were not very optimized. And I know that they're not optimized because they didn't use SRAM buffers, for example, but still it's a large area, as we will see in some other slides. So the key question that we may want to ask when you're actually moving from off-chip to on-chip, or even off-chip, I think, actually, is can we get rid of buffers? This may sound very simple. Actually, this is really an old idea. In the 1960s, as I said, hot potato routing was developed. And hot potato routing is, you don't have buffers, you just pass on the hot potato to someone else. You don't care who you pass on to. You just nobody wants to hold on to the hot potato because they will get burned, right? That's a good analogy. And people actually considered not having buffers on the internet for some time, and they quickly dismissed the idea. Why? Because they thought the curve would look like this for the internet. So if you actually have large buffers, you get significant throughput. And if people are actually loading the internet a lot, then you want large buffers. And also there's software management of buffers in a lot of the internet routers. So you can manage them in a more flexible way. So the key question is if your network can tolerate this difference between small buffers and large buffers, maybe you don't want a lot of buffers, right? Okay. Yeah, basically, it's an old idea, but it's surprisingly actually a lot of works assume buffers without even questioning that assumption for a long time. So we wanted to question that assumption. And the first thing the ask is, okay, we have buffers, the curve looks like this. We have no buffers, the curve looks like this. We know that the curve will be different, but how much different? Right? How much throughput do we lose? And how is latency affected if we actually go bufferless? And up to what injection rates can we use bufferless routing? And are there realistic scenarios in which, in a network on chip, you operate below those injection rates that are reasonable for bufferless routing? So that's the idea. Of course, you can do these studies. If you have a good simulator, if you have good workloads, you can do all of these studies, and that's what essentially we've done. Of course, on top of that, can we achieve energy reduction? If so, how much? Can we reduce area, complexity, etc.? And I believe all of these make sense when you reduce the bufferless. So it's in the paper. I have assigned the paper, but I'm not going to go through this one in detail. I'm going to talk about it quickly and then discuss some of the things that try to make it real. So okay, bufferless routing, the key idea is to always forward all incoming flits to some output port, as we've discussed. If no productive direction is available, you send it to another direction. Packet is deflected. And as I said, it's an old idea, right? And you've already seen this animation a better way. So if you have bufferless, one packet can get deflected. If there are two productive output ports that you can send both packets to, that's fine. You send both of them to the productive output ports. That's good. But if there is no productive output port for a packet and there's an empty output port, you just send that packet. So if you look at a modern router, it looks like this, and the buffers are over-provisioned in general. So basically, we want to get rid of that. And hopefully that enables us to get rid of this, and hopefully that enables us to get rid of that as much as possible, right? That's the hope. The reality is going to be different. This paper is very optimistic in its assumptions, and then you move to the reality with the next work, as we will discuss. So basically, this paper introduces an arbitration policy that ranks the flits that are incoming and does port prioritization. So the reason there is a ranking that happens over flits is because we want to ensure live lock freedom, right? If you're bufferless, you may actually have live lock in the network. Actually, you get rid of deadlock because deadlock doesn't happen anymore because you're not waiting for buffering resources. Deadlock usually happens because you're waiting for a buffer and buffer is occupied by someone else and you have the circular dependency on buffers. Once you get rid of buffers, deadlock goes away. But you are left with live lock now. You need to ensure that each flit goes to its destination in a bounded amount of time. So basically, the arbitration policy changes now. You have it creates a ranking of all incoming flits, and for a given flit in this ranking, it finds the best free output port, and it applies this to each flit in the order of ranking. So now the question is, how do you rank the flits? And that becomes a hairy issue actually in the design. So each flit in this case is routed independently. It's called Flit-less. So we get rid of some of the benefits of wormhole routing. The paper discusses wormless, which is interesting, but I'm not going to talk about that. Basically, how do you do wormhole routing in a bufferless network? Not so easy, because you need to break the worms actually sometimes, because sometimes you cannot buffer anything, right? Meaning that you cannot really buffer any part of the, sometimes the body flit needs to become the head flit basically in a worm. But you can read the paper for more detail of that. But if you're assuming that you're doing the simple thing is each flit is routed independently. You need to ensure each flit gets to its destination. And how do you ensure that? So oldest first arbitration is one way of doing that. Basically, it guarantees that the oldest flit injected into the network arrives to its destination because it's always prioritized by this ranking scheme. That sounds good, right? And you do oldest first ranking, and you assign the highest ranked flit to the productive port is possible. So hopefully the highest ranked flit always gets the productive port, which is true in a router. Otherwise, you assign, if the productive port is not available for the flit with the given rank, you assign it to a non-productive port. And that's how the deflection algorithm works. We're going to get back to this and deconstruct this because this oldest first ranking is not actually easy. Actually, this arbitration becomes more complex than an existing virtual channel router. If you think about a virtual channel router, arbitration is not that hard. Buffering is hard, flow control is hard, but arbitration is not that hard. You just look at the queues, heads, and then you pick one to go to a particular output port. Yes?
Do you ensure when you do the deflection of flits that they arrive in order?
That's a great question.
Then you would hope that it arrives in order when all flits arrive.
Yeah, that's a great question. So they don't. So bufferless routing doesn't help you with in order. So it basically changes the potential order of arrival. But we give up in order delivery. Yes. But you can reassemble the packet on the receiver side because you have flit IDs for a given packet. You know which ones you're missing. It's very similar to TCP, for example. You can reassemble. Essentially, this requires reassembly buffers, as we will see. So the buffering requirements in the receiver actually increases, but there is an easy way to fix that because you need to. Usually, what happens is in the receiver, you're waiting for a cache block, let's say, in an on-chip network, 64 bytes. You normally wait for the entire cache block before you do something with it. So you have a buffering allocated for the entire cache block. Let's say it comes in 8 flits. You wait for all of the 8 flits before you do something with it. Does that make sense? Because you usually write to your cache at the ground layer to have a cache block. So we're going to exploit a lot of on-chip advantages. But that's a very good point. If you think about wormhole routing, it guarantees in-order delivery of the entire flit. And if you're the entire packet, if you're relying on that for some reason, that is broken here. But you can reassemble. And I think this is also a good question. Do you really need that sort of in-order delivery requirement? Personally, I don't think so. I think you can you don't really need it, because when do you really need it? Because if you want to do it for coherence reasons, most of your coherence packets are only a single flit, usually. They're control packets, and there is no breaking of the single flit in this case. So they arrive in whatever order they arrive. And most of your larger packets that are broken into flits that lead to this out-of-order delivery are data packets. And in general, you don't really care about how you deliver the data, right? Actually, we break that even in the memory systems, right? We do a critical word first fetch from the memory system. So we try to fetch the critical word first. That may affect the delivery, but I think you can add priorities on top of this to say, oh, this is a critical word, so try to prioritize it. Okay, so the question, let's back up a little bit. So where can we apply this to? So this can be applied to most topologies. Basically, your number of input ports, I don't know what happened here. Is it a comma? That thing is weird. Basically, your number of output ports should be greater than or equal to your number of input ports for this to work, right? If your number of output ports is less, then you have a problem, because then you need to buffer, right? So I don't know what happened. Let me see if that's the case. Oh. Okay, it's the same. Interesting. Anyway, we'll have to fix that. That's greater than or equal to. And every router should be reachable from every other router, of course, because you're misrouting things right now. Flow control and injection policy. This is completely local now. Flow control. There is no need for signaling an upstream or upstream router that you have buffers, because there are no buffers. And you inject into a router whenever an input port is free. Basically, whenever you're injecting, you need to look at, we discussed this with the crossbar earlier. You need to look at all of the input ports, and if an input port is free, then you can inject. There is no deadlock, as we've discussed. Every flit is always moving. That's good. And if you use all this first ranking, there is no live lock also. Otherwise, you could run into live lock. Okay, so let's take a look at advantages and disadvantages of this sort of network. No buffers, purely local flow control, simplicity, no credit flows, no virtual channels, simplified router design, hopefully, but we'll get back to that. No deadlocks, no live locks, assuming all this first. Adaptivity, actually, this is actually interesting. You get natural adaptivity because of this deflection, right? If you're in a congested area, packets just simply get deflected and they go around that congested area, hopefully. So that's good. The routing algorithm has built-in adaptivity. And router latency reduction, but we'll get back to that in a little bit. This paper is very optimistic in its assumptions. It's looking forward, but it's not thinking about implementation a lot. And you get a lot of area savings because you reduce buffers. But there are disadvantages, of course. You increase the latency now because deflection actually routes around, and that increases the packet latency, right? Especially when you have congestion. So at high congestion levels, this may not work really well. That's why if you have large buffers, your saturation throughput is higher. If you have small buffers, your saturation throughput is lower, right? So at high congestion, you have a problem, basically. Your latencies are high. Your bandwidth is also, saturation throughput is low. Now, this goes back to the point that you make. You need to have buffering at the receiver right now to reassemble the packets that are coming out of order in its flits. And if you're doing flit-based routing, you need to have header information at each flit. So there is some overhead that you add to the network to carry that header information in each flit. If you look at wormhole routing, buffered routing, only the header flit needs to carry the header information. All of the other flits don't need to carry the header information. Now there's also the interesting question there, what fraction of your packets are single flit packets and multi-flit packets, right? Control packets are usually single flit packets, unless you have a really narrow network. Usually they're not really narrow on chip. Because your control packet doesn't need to provide more information than, let's say, 8 bytes, right? You can encode a lot of information in 8 bytes or 32 bytes. But if your data packets are usually the ones that are longer. Okay, so all this first arbitration is complex, as we've discussed, and we're going to discuss more. And quality of service also becomes more difficult because you eliminate the buffers. One of the nice things about buffering is it helps you with quality of service because it keeps the packets. You can analyze them, and then you can decide, okay, I'm going to take it out of this virtual channel and take it out of that virtual channel. Now you need to do all of that quality of service while the packets are moving in the network, right? Okay, there's also impact on energy. So router latency comes let's take a look at an evaluation over here. This is the bad news. Bad news is usually comes with bad patterns. Actually, there's a hotspot pattern that's analyzed in the paper that may be even worse, but hotspot is not good for, in general, any network, so the curves look similar. So this is uniform random injection, and this injection rate in terms of flits per cycle per node. And as you see over here, this is the best baseline. It has ample buffering. It's minimal adaptive routing. It doesn't do non-minimal adaptive routing because we don't want to solve the live lock issues over there. But minimal adaptive is doable. And as you can see, it's far beyond any other network over here. And these are the bufferless networks. They're all different versions of bufferless networks. One of them has 1 cycle latency, 2 cycle latency, flit-based routing, worm-based routing. Worm-based routing we didn't discuss. You can read the paper. And the paper is a required paper, so I would recommend reading it. So it doesn't look good, right? Yeah. But if you actually look at real workloads, it looks much better. Because real workloads are actually not uniform random. And they don't inject this much. This is basically a lot of injection. This is almost 0.5 flits per cycle per node. Then the question is, what is reality? What is reality? Then you simulate with the real workloads, and it turns out it's not. I'm not going to go into this in detail, but basically, bufferless and buffered networks have similar performance in terms of real workloads. And this is moderately intensive. We assume perfect caches in this case, perfect L2 caches, not perfect L1 caches. Because if you actually don't assume perfect caches, it turns out your network is even less loaded. And this is an observation that a lot of people made. There are these networks on chip. Usually they're not used. Usually they're not very loaded. Because you send you miss in the cache, and then you have communication between the L1 caches and the distributed L2 cache, let's say. And then sometimes you hit in the L2 cache, you get the messages back. When you miss in the L2 cache, or L3 cache, you go to memory controller, and that flits get decommissioned for a while because now it waits for the memory latency, right? So it's out of the network that's on chip. So that's why there's not a lot of load on this network. Not all applications actually insert a lot of load. Some applications do, of course, and we will see that in a little bit. So that's one of the key observations. There's not a lot of load on the on-chip network. As a result, you have very little performance degradation with bufferless routing. And this paper is very optimistic in its results. So we're going to look at more realistic results in a little bit. Yeah, okay. And let's look at the energy over here. So you get significant energy improvements, as you can see over here. So this is the breakdown of buffer energy. So these are buffered networks. This DO, dimension order routing, min-AD, minimally adaptive routing, and ROM is a version of Valiant's algorithm actually that does oblivious routing. So as you can see, routing matters relatively little in these networks. And if you have a lot of buffering, buffers consume a lot of energy. Link energy is like this, and there's a router energy also. Now if you get rid of buffers, you essentially consume little energy. There's some little buffering that you still have over here. Link energy increases a little bit because now you're doing more deflections. And router energy also slightly increases because you're doing more deflections. You're exercising more routers for an average packet. So that's the trade-off basically. You get rid of almost all of your buffer energy, but you increase your link energy and router energy because deflections cause a packet to travel more hops, more links, and more routers. But overall, the energy looks reasonable. Okay, so these are the key observations. Injection rates are not extremely high on average because the network is also first of all, L1 caches act as a filter, and the network is also self-throttling. You cannot keep injecting into the network because at some point you run out of your miss buffers, right? MSHRs. Essentially, for bursts and temporary hotspots, we're using network links as buffers. So the conclusions of this work is this basically. For a wide range of application and network settings, buffers are not really needed in the network on chip. As a result, if you eliminate them, you get significant energy savings and significant area savings. Area savings is, we will see better area results in a little bit. You get simplified, hopefully, router and network design. Certainly network design, but router design actually becomes more complex, and we're going to go into that. And performance slowdown, performance loss is actually minimal. If you're optimistic, it can even increase because the optimism is that if you don't have buffers, you can actually make your router even faster. But we're going to see that that's not actually correct. So essentially, there's a strong case for rethinking network on chip design. And At the time we wrote the paper, we suggested that future research should focus on bufferless networks and figuring out how to make them work for different things. Okay, and that's the paper. Any questions so far? Okay. So maybe I'll take a break before I start the next one. But basically what we're going to cover is some issues in bufferless deflection routing. Live lock is a key issue, and live lock is the one that causes the router to be complex. And we're going to think about different algorithms for live lock. This is something that people have not thought about. How do you actually guarantee live lock freedom with minimal complexity? And we're going to talk about that. And also there are issues like, okay, not all workloads have these low loads. What if you have a lot of high injection rates into the network? How do you handle that? We're going to talk a little bit about that, but maybe not go into the full detail. There's a lot to be done over here, actually. And then on top of that, how do you actually provide quality of service and fairness? We're not going to talk about that within the context of bufferless networks, but there's a lot of interesting ideas here also. So as one of you mentioned yesterday, quality of service and fairness is actually important in any type of network. Okay, so let's take a break right now for 10 minutes. Be back at 25 past, and then we'll continue. Okay, so we've been talking about bufferless routing, and let's talk about how to make it more implementable and real. And we're going to tackle complexity even more. So let me pull back a little bit. I think you can always design a system with a lot of over-provisioning, a lot of buffering, but you run into, then you can handle congestion really, really well, and you can handle high load really well. That's great, but it comes at a cost. Energy efficiency, especially, and complexity, right? You can also have no buffers or something that's really simple over here. Your performance isn't very high, especially at high loads, but maybe you're simple. The question is that really simple, right? That's the question that we wanted to answer. And it's surprisingly, there's a lot of work that covers this space, which is a lot of buffering, a lot of over-provisioning, making things more and more complex over time, handle, better workloads, that's good. But there is very little work that we found on this side where, there's no buffers. How do you actually handle the issues that arise when you don't have a lot of buffers? That's why we were actually the first ones to discover that the router actually becomes even more complex when you don't have buffers. And that was actually interesting because in the first paper we assumed that router is actually going to become more simple. But it actually becomes more complex, as we will discuss. Okay, so we've already discussed this. We've already seen significant potential for bufferless routing, significant area reduction, minimal performance loss with real workloads, not with intensive patterns. Unfortunately, there are unaddressed complexities in the router. It turns out this complexity in the router at least long critical path and large reassembly buffers, as we've discussed. So we're going to get rid of that. Now, basically, we'd like to obtain the benefits as much as possible while simplifying the routers as much as possible in order to make bufferless network on chips more practical. So what are the problems that a bufferless router must solve? First of all, it must provide live lock freedom, and we knew that very well. A packet should not be deflected forever. And it must reassemble packets upon arrival because of this reordering that we've discussed. So if you look at a high-level view, a bufferless router looks like this. It has deflection routing logic, it has a crossbar, and it has reassembly buffers and after the ejection logic. So it doesn't look that bad, but it turns out this is not simple. So the live lock freedom should be handled somewhere over here, and the packet reassembly should be handled over here. It's not packet reassembly is not that hard actually, as we've discussed, right? But you need buffers over there. And actually, the original paper discusses there's a trade-off. You get rid of buffering here, but you increase the buffering over here. The question is, do we really increase that buffering? As we will see, you could actually use the on-chip buffers. If you're integrating your network with the core, then you can actually use the on-chip buffers. So first of all, how do you provide live lock freedom? You sort the packets by age, oldest first routing, and then assign in age order to the output port. For each output port, you decide what is the oldest flit that wants that output port. That's the output port arbitration. It turns out this leads to significantly longer critical path than a buffered router. If you think about a buffered router, you don't need to do, first of all, you don't need to do oldest first routing at all, because you don't need to handle the live lock freedom problem. So a lot of the on-chip buffered routers or off-chip buffered routers, what they did was they did round robin across the virtual channels. So round robin basically easily picks which virtual channel is going to be prioritized over the other one. So that's relatively easy. You don't need to sort anything by age. Okay, so reassembling packets upon arrival. Essentially, reassembly buffers must be sized for the worst case, as we will see in a little bit. And this could be very large per node. I don't think 4 kilobytes is that large, but as network size increases, this can become larger. So let's tackle these problems in a little bit. Let's understand these problems a little bit more. Because this leads to algorithms, I think. The first one, how do you provide live lock freedom? It's essentially algorithms. The first question is, what stops a flit from deflecting forever? Right. You can timestamp all the flits. All the flits are assigned their desired ports. Of course, if 2 flits have the same timestamp, you need to have a tiebreaker. It could be the node number that's injecting it, for example. So essentially, this leads to a total ordering among the flits, right? And this total order, as long as it's obeyed by all of the routers, that's great. The oldest flit always has guaranteed progress, and at some point it gets out of the network, it becomes, the next one becomes the oldest, so it's guaranteed progress, ... If it hasn't reached its destination, basically. Some of them may reach their destination without being the oldest, right? Actually, most packets, most flits do that. They don't become the oldest before they reach the destination. Depends on the congestion patterns in the network. So new traffic that's injected is clearly the lowest priority at that time. So what is the cost of this? So if you actually try to design this router, you need to have a sorting network, first of all. You need to figure out the ordering of the flits by age. So it's a long latency sorting network. This is one example. You have 3 comparator stages for 4 flits over here. These are the 4 input ports. And assume that the highest priority is 1. So you basically want to sort them. Well, essentially that's the sorting network. In the end, you get 1, 2, 3, 4. And you can design this. Right. Okay. You can run through the animation yourself and figure out what's happening, basically. Okay. Sounds cool, right? But basically, this is actually a router by itself also, if you think about it. It's really a switch by itself. A switch that has some intelligence that makes a decision. Yeah. Okay, anyway, I'm not going to go through this in detail now. So the downside is this is a long sorting network. That's, first of all, you sort it. Now you figured out which ones, what is the ordering that you have over here. Now 1, 2, 3, 4, the highest priority is always here, the lowest priority is always here, right? Now you need to do something else on top of that, right? After sorting, you need to assign the flits to output ports in priority order. For each output port, you need to essentially do the assignment. The port assignment of the younger flits now depends on that of the older flits. So there's a sequential dependence in the port allocator. So let's assume that you ordered the flits based on age. This is the oldest one, this is the youngest one. The oldest one is requesting east, and it's granted east. This is one way of thinking about it. Of course, there are multiple potential designs that you can do. Now, for the second one, what's available is not east anymore. It's north, south, and west are available. If the second one is requesting east, it will not be able to get it. And if it's only requesting east, it will be deflected. So, and then north is picked somehow. And then south and west become the only ones that are available to this one. This one is requesting south, that's good, it's granted. And west is the only port that becomes available for this one. And if it's requesting south, too bad, it's deflected. Right. So essentially, in this case, 2 flits are deflected. But the deflection decision is dependent on the previous allocation that you do. Because you have availability of ports, and you basically need to send stuff to ports that they don't want to be sent to in a bufferless network. So basically, this is what the port allocation and sorting looks like. You have a priority sorting mechanism, and they have a port allocator. And because of the sequential dependence and the long latency, you get significantly longer critical path. If it's 43%, it's actually optimized. It could be much longer than a buffered router. The question is there a cheaper way to route while guaranteeing live lock freedom? And the answer is yes. What is really, the first question is, what is really necessary for live lock freedom, right? Do you really need all of that total order across all of the packets that you see in the network? And the answer is no, you don't need that total order. So in this case, if you look at what we've done before, is all age-based priorities lead to total order. And there's no need for total order if you care about live lock freedom at low cost. Basically, all you need to guarantee is to pick one flit and prioritize it until it arrives to its destination and ensure any flit is eventually picked. Let's call that the golden flit. It's actually packet-based. If you read the paper, you will see that, but let's assume flit-based. Let's call that the golden flit. So you pick one flit to be golden and prioritize until it arrives and ensure that any flit is eventually picked. And that's the simplest live lock freedom mechanism that we could come up with. I'm not sure if there's anything simpler than this at this point. Of course, you can make it more complicated, as we will see in a little bit, to make things a little bit better, but this is all you need. So now the question is, how do you select the golden packet or golden flit? Now you can actually be simple here because this is a distributed thing, right? You have actually many potential nodes that are injecting into the network, and you want to actually ensure that any flit that's injected in the network at some point is guaranteed to become golden. That's the idea. So what's the simplest thing that can you do here? Well, first of all, a given packet stays golden long enough to ensure arrival. That's the first thing, meaning that assuming that you prioritize this flit in every single router, how long should you need to prioritize it for? And that's essentially the maximum no contention latency, right? So for that period, you need to keep a flit golden because you're guaranteeing in the routing logic that golden flit is always going to be prioritized. That's good. And this is going to make the logic simple because you just have golden, not golden. That's the only difference. Okay. And then the question is which flit becomes the golden? So this answers the question when a flit becomes golden, when the golden flit changes. The golden flit stays golden for the maximum no contention latency. That's the maximum distance between source and destination and how long it takes. And also, which flit do you pick next to be golden? So in this case, we actually made it really simple. You basically look at all possible packet IDs that could be present in the network, and you rotate the selection in a deterministic manner, static manner, for simplicity. So you know exactly, in an on-chip network, again, you know what could be in the network, right? So you basically, if you look at a packet, you have source, destination, and request ID. And when you're injecting into the network, essentially you know the ID of the flit that you're injecting into the network. It has a source ID and it has a request ID, and that's unique. Basically, for every source, when you're injecting, it needs to keep track of the request ID because it needs to get a response, or it needs to keep track of it for some other reason, right? That's what happens in a cache coherent network. You stamp it with the source ID, and then you have a buffer when you're injecting that tells the request ID. And that's unique across the entire network. What you can do now is you can start a deterministic rotation that basically says, I'm going to start with source 0, request 0, and I'm going to designate that as golden. Designate that slot as golden. And I'm going to do it for, let's say, maximum no contention latency cycles. From cycle 0 to cycle 100, source 0's request 0 will be golden. At cycle 100, I'm going to pick source 1's request 0. At cycle 200, I'm going to pick source 2's request 0. At cycle 300, I'm going to pick source 3's request 0. At cycle 400, I'm going to pick source 0's request 1. Basically, you're really cycling through all possible requests that could be in the network. And you're prioritizing each of them for the maximum no contention latency. And every router is aware of this. Every router obeys this because they're designed that way. Does that make sense? Now the question is, of course, when you pick source 0's request 0 to be golden, that may not be in the network. Because you're really going through a static schedule. Even though a source may not be injecting anything into the network, you say, okay, this particular slot that could be in the network is golden. Doesn't matter, right? You basically wasted that golden slot. Nobody's in the network. The golden packet is really not in the network. That's fine. That slot is designated still as golden. But at some point, every slot will eventually become golden. Does that make sense? So if a packet is injected into the golden slot, it'll be delivered, basically. That's the idea. And if it doesn't get delivered, if there's a race condition, it gets injected in cycle, let's say, for example, if source 0 request 1 gets injected in cycle 450, it has only 50 cycles to be delivered. It'll be golden for only 50 cycles. If it reaches its destination, that's fine. If it doesn't, yeah, maybe it will need to wait until its next turn to become golden, right? It's very simple. It has a bound in terms of latency, and the latency bound is very long. It's basically, but the hope is that you don't rely on this live lock freedom guarantee very often. If you're relying on this live lock freedom guarantee, then you have some other problems in your, with congestion in your network anyway. That's the idea. So this just is there to guarantee correctness in the end. So that's the other high-level idea. Correctness guarantee doesn't need to be something extremely complicated if you don't need to exercise it very often. Okay. So I'm giving you the idea now. Basically, you at cycle 500, you go to source 1 request 1, 600 source 2 request 1, 700 source 3 request 1, 800 source 0 request 2. If you have 4 sources, that's what you do. And if you have, so let's assume a realistic network. If you have, let's say, if you're able to inject 128 flits into the network, and you have 16 sources, then you have 16 times 128 slots that you cycle through. And you do that, and your worst case latency you can calculate based on that if you have live lock issues. Okay, now we've figured out which packet becomes golden. Let's see how we can actually route that. Basically, you need to only properly route the golden flit. I'm switching between golden packet and golden flit, but they're really the same thing in the end. If you're doing flit-based routing, it's the same thing. Basically, that simplifies the router quite a bit. Now you don't need priority sort because you don't have priorities. You just know which one's the golden flit. And you don't need sequential port allocation because we're going to be more liberal in what we do with our ranking. And you can actually improve upon this, as we will see later. So first, let's route the golden flit in a 2-input router. We're going to build a permutation network that actually does this routing. So you basically, the function of this 2-input router is, in step 1, it picks a winning flit. And winning flit is, if one of the flits is designated as golden flit is the winning one. Otherwise, you randomly pick one of the flits. You can do better than random if you want to minimize deflection, for example, but this work wants to be as simple as possible. And then it steers the winning flit to its desired output port and deflects the other flit. Well, not necessarily deflects, because it may not actually be deflected. The desired output port may be that one, right? Basically, only the winning flit gets its desired output port. The other one, we don't care. Well, there's no choice anyway, because it's 2x2 router. So a golden flit is essentially always routed towards its destination in this case. So let's take a look at an example over here. So this is a permutation network that's consisting of 4 2x2 routers. Each block makes decisions independently in this case, so the router becomes actually simpler also. And deflection is now a distributed decision across these. So let's pick one as golden over here. You have these, there are no priorities. This one is golden because it happens to be in a slot that's golden, designated as golden. And we know that, every router knows that, so it has a bit set saying that, okay, at this point in time, this is golden. So let's take a look at how this one does the routing. There's no golden flit over here. As a result, this one picks one of them to be, this one picks one of the input flits randomly to be the winning flit. Let's assume that the red one wins. If the red one wins, the red one's destination is over here, and this 2x2 router knows that it needs to route this to this output port. So it basically does a swapping decision. And the green one gets this output port, which in this case is a productive output port if you look at the internal permutation network. So the router itself is a network, actually, if you can see over here. But it's a simple network. So let's take a look at this one over here. Remember, this one's golden. So this particular switch says, oh, the winning flit is the golden one, so I'm going to prioritize it. So how will it prioritize it? It will basically give it its productive output port. The yellow one wants to go here. The blue one is sent over here. So far, it's okay because blue one can potentially go here. That's good. There's no deflection yet. Well, deflection happens at the end anyway. Okay, so basically now this is what happens. And then in the second stage, let's take a look at what happens to this router. None of them is golden. As a result, you randomly pick one of them that wins. The green wins. And green wants to go here. That's good. It gets prioritized. And blue one happens to go to its output port also. That's good. So nothing is deflected over here. That's good. If you look over here, yellow one is golden. And yellow one wins. It goes to its output port. And the red one gets deflected because it really wants this output port, but it has to go through this one. Make sense? So it's a very simple router that makes deflection a distributed decision. Of course, you can optimize it better because some of the decisions are made randomly right here. So now we've gotten rid of both of these and replaced it with something that looks like this. That's much simpler. Okay, so this is our permutation network-based pipeline now. Injection and ejection in this work is handled in a different way. It's not sent into the router, so that makes life a little bit easier. But you can think of injection and ejection also as another port over here. But if you handle it in a different way, it actually makes life easier. And you can read the paper for more detail over here. Okay, the next problem is packet reassembly. Let's take a look at some other problems that are caused by packet reassembly. So reassembly buffers need to be large, basically. In the worst case, every node sends a packet to one receiver. That's like the hotspot pattern, right? So you have all these nodes, n sending nodes, and one packet in flight per node, and the receiver requires ON space now. So why can't we make the reassembly buffer smaller, you may ask? So what happens if the reassembly buffer is too small? Let's take a look at that case. You have many senders, you have the network, and you have reassembly buffer that looks like this. You have 2 flit packets and 2 packets that could be reassembled in the end. Let's assume that senders are sending their packets, they're coming, they're arriving, and this one allocates one of the reassembly buffers. Now it's waiting for its match, which is the second flit in the green packet. And this one also gets allocated, received by the reassembly buffer. Now the reassembly buffers are waiting basically for the blue packet and the green packet, the second flits. Now let's see what happens in the network. The yellow one comes into the network. It arrives at the receiver. It cannot be ejected because the reassembly buffer is full, because there is no buffering space. So what does it do? It gets deflected, so it gets circling around the network. Now things start getting injected into the network. Many senders are injecting stuff, and it turns out none of them can get ejected because they're destined to here. At some point, network becomes full. The senders cannot inject, and this cannot eject because it's waiting for the blue one and the green one, and they have not been injected yet. As a result, you have a deadlock. This is a protocol level deadlock. It's not really a buffer level deadlock because there are no buffers in the network. But you cannot eject from the network because there is not enough buffering in the destination. And you cannot inject the things that would release the buffers into the network because there are not enough links in the network now. As a result, you have this deadlock. Right? Make sense? So forward progress is limited. And this is an example of a protocol level deadlock. Essentially, because you're not handling the protocol really well, you have a deadlock. Okay, so let's take a look at how we can eliminate this deadlock. It's not that hard to eliminate actually, but the solutions that you develop will affect your efficiency and performance. So let's assume that what if you want to ask permission from the receiver before you send a packet. Every sender does that. So the idea is you have some reassembly buffers, limited. The sender first needs to reserve the slot, get the acknowledgement, and then send the packet. This way you guarantee that there's a reassembly buffer allocated for you before you send the packet into the network. It's very conservative basically. So you basically ask the receiver, can I reserve a slot in your reassembly buffers? Receiver says, okay, I reserved it for you. Now you can send it. So acknowledgement. And then the sender can start sending packets. Of course, deflection routing happens in the middle. Now the downside here is it adds additional delay to every request, an additional round trip delay actually. You need to send the request and then you need to receive the acknowledgement before you can send the packet. Not a good idea. This actually is terrible in general, especially if your network is not loaded, especially if this is not a problem, right? This is not a good common case design. Okay, so another way of escaping deadlock is by dropping. So we're going to have to resort to dropping, unfortunately. So you cannot just purely have deflection, but you need to have some sort of dropping on top of this. So sender is optimistic in this case. In the previous case, sender was pessimistic. Now we want to have an optimistic sender. It assumes the buffer is free. If it doesn't, the receiver drops and NACs, or negative acknowledgement. It sends a negative acknowledgement to the sender, and then sender at some point retransmits. So let's take a look at this one. So the sender first sends, and the receiver is going to drop a negative acknowledgement, and some other packet will complete. We're going to retransmit the packet. We're going to get an acknowledgement, and then sender freeze the data. So sender is going to send, but it's not going to be able to deallocate its buffers. That's not a good idea anyway in general. Unless you have a completed request, don't deallocate your buffers. Okay, the receiver says, I'm full, I'm dropping, and sends a negative acknowledgement back to the sender. And the sender now, at some point, retransmits and hopefully gets a buffer. In this case, it's got lucky because there was something free. But that may not happen. You could keep retransmitting, and you may actually get NACs. And then the receiver acts, and then the sender now can clear its data because it doesn't need to transmit again over here. So that's the idea over here. Now there's a downside. The big upside here is in the best case there's no additional delay because you're optimistic in your transmission. But transmit buffering overhead you have for all packets. You could actually deallocate some of them earlier, but we have that buffering overhead and potentially many retransmits. So you could actually, if your network is congested, you keep retransmitting. Of course, this depends on your threshold of when you decide to retransmit. There are thresholds that need to be optimized here. But this actually leads to more congestion in the network potentially. So not good. So the idea in this work is to do retransmitting only once. So basically retransmit only when space becomes available. You're optimistic at first, unless you're proven wrong. So receiver drops the packet if it's full and notes which packet it drops. And when space frees up, receiver reserves the space so that retransmit is successful. So you only retransmit once. And then receiver notifies the sender to retransmit. So let's take a look at this. Sender is optimistic initially. It sends its packets, its flits directly to the receiver. Receiver drops. Receiver makes a note of which node's request it dropped. Node 0's request 0, it dropped. It basically doesn't tell anything to the sender for some time until something becomes free. And once that thing becomes free, the receiver reserves that particular slot and tells the sender, now please send me this particular request that you sent, but I happen to drop. And then the sender now can send that, and the slot is reserved, so it doesn't need to retransmit again. That's the idea over here. So it gets the best of optimistic and pessimistic protocols, except there's of course still trade-offs. It's somewhere in the middle. But at least it doesn't have the delay initially, and it doesn't have a lot of retransmits. Okay, so that's one example protocol that you need to handle. So basically, in the end, you cannot get rid of buffering because you have to put these packets somewhere. The question is, where do you do the buffering? And here the buffering is actually only in the edge nodes, senders and receivers. Internally, the network doesn't have buffers, except for pipeline latches, of course. Okay, so can we actually eliminate the buffers even more? And the next realization is that actually these buffers already exist. So what are those buffers? You have missed status handling registers. Basically, whenever a node sends a request, it keeps a record of that. And we've seen it before. Missed status handling register is an example of it. You have a list of outstanding cache misses. And this essentially has a lot of information, the data buffer. And you can essentially we have reassembly buffering for free. You basically, whenever you receive a part of a flit, you place it into part of the data buffer that you already have for outstanding cache misses. So you actually don't need this additional reassembly buffering. Of course, if you're separated from the MSHRs, if you have a completely different separate network interface, then you can do additional buffering over there. But there's no need in an on-chip network. You can actually use the MSHRs as your reassembly buffers. So that's the idea over here. So basically, we got rid of these reassembly buffers. They're really your miss buffers, MSHRs. And we've already gotten rid of this part. Okay. So basically, this is the idea in the end. This is the baseline bufferless deflection router that we started with. It had large reassembly buffers and it had this deflection routing logic. We got rid of the deflection routing logic which had long critical path because it needed to sort it by age and it needed to allocate ports sequentially. We used the golden packet and permutation network ideas to replace it. It's a different deflection routing logic right now, but it's not shown there. And then we got rid of the large buffers for the worst case with the idea of retransmit once and using cache miss buffers as the reassembly buffers. And then your router looks like this. So it's a much simpler router right now. So the question is what is much simpler? And what kind of performance do you get out of this much simpler router? Okay, so there's some evaluation methodology. You can take a look at it. It's in the paper. And there's buffered baselines and bufferless baselines. Bufferless baselines, bless in this case. And there are a bunch of workloads, multi-program, multi-threaded. We can take a look at this. And there's methodology for hardware modeling also. Of course, you need to model the hardware routers. It's Verilog models for various routers over here and power. Okay, so let's take a look at performance first. What is the performance degradation that you have going from an aggressive buffered network to bless to chipper? And if you look at the performance degradation, chipper is worse than bless. Actually, bless has optimistic assumptions, as we will see. This doesn't take into account the router latency increase because of bless. That's okay. But if you look at it, there are some workload. On average, the performance loss in multi-program workloads is about 13%. And in multi-thread workloads, it's even lower. So it doesn't matter almost over here. But the workloads that do not exercise network a lot, the performance loss is relatively small. It's about 3.6%. And these are much more realistic results than the previous work. The workloads that exercise network a lot, very, very high congestion levels, you actually lose a lot of performance. It's about 50%. Now you could argue that these may not be extremely realistic workloads because this is a stream workload, for example. Almost every access to the cache miss. And as a result, you're really exercising the network. And we actually have perfect L2 caches, so we don't have anywhere to escape. So this is really stressing the network. This is one of the worst case evaluations. So I don't think this is actually very, very realistic, but if you want to evaluate to the extreme, this is the extreme evaluation, I think. So yeah, I don't think many people run these workloads in general, although there are few cases that they exist. So most of the workloads are, I think, in this domain over here. Okay, and multi-thread workloads, these are workloads that are multi-threaded, so they don't exercise network a lot, as we expected. So you get minimal loss for low to medium intensity workloads. So let's take a look at power reduction. This is power, buffered, bless, and chipper. Chipper is actually much more power efficient than bless because router power is reduced compared to bless. So the power reduction is about 55%. Even on workloads where you lose performance a lot. So you basically get a lot of power reduction. So this is very good for power in general. And that's true even more for multi-threaded workloads because these workloads don't really exercise network, but you have a lot of buffers that are just wasting power in the network. And watch the scale over here. This is a much higher scale than this one because this is the network power over here. And if these workloads are not exercising network, their network power is inherently lower, right? Okay, so you basically get the majority of the power savings from removing buffers, and you can read the paper for more detailed breakdown. And you get slight savings from bless to chipper because the router is much, less complex right now. Let's look at the router area and critical path. So all of those optimizations that we've discussed, how does that affect? So if you look at the router area, you get significant reduction compared to a buffered router, about 36%, which is similar to bless. Bless also gets rid of a lot of the buffers. But this is a little bit more because the routing logic is also less complex. If you look at the critical path, bless is not so good, but we've done all of this to reduce the critical path actually. So the critical path is pretty much on par with a buffered router at this point. So you don't lose the critical path or frequency in any way. Okay. Okay, so I've given you the ideas. I think I don't need to go through this. Maybe I will, actually. So there are two key issues in bufferless deflection routing, very fundamental. Live lock freedom and pushing of the buffers to the edge nodes, packet reassembly. And bufferless deflection routers, previously, as we discussed, were high complexity and impractical because of all this first prioritization. And they didn't have end-to-end flow control for reassembly. As a result, they were actually prone to deadlock also. It's not just high complexity, but they were also impractical because you need to solve this deadlock issue with limited number of reassembly buffers. So this idea of chipper is essentially a more practical deflection router. It gives you golden packet prioritization to enable short critical path. This retransmit once protocol enables deadlock-free packet reassembly. And cache miss buffers act as reassembly buffers. As a result, you actually don't need to have additional buffering on the edge nodes. And as you see, the frequency of the router is comparable to buffered routers at much lower power and area cost. And minimal performance loss at workloads that have low to medium intensity on the network. Any questions? Okay, so you can read the paper. It's not a required paper, but if you want to really look at a real bufferless router, I would suggest looking at this one. Then the question is, okay, are we done? We're not done. And I think actually this direction has a lot more potential going forward, especially in SoC, system on chips, where you don't have a whole lot of traffic on the network, but you do need a network that connects all of the components. And you do need to be extremely power efficient. I don't think it's a wise thing to do to actually spend a lot of your energy on buffering. So I think it's good to actually look into how to make this even more practical going forward. And that's the next work over here. Actually, I will go into this in a little bit more detail because this is fun. So basically, we're going to introduce a little bit buffering. So if you look at the spectrum of no buffering and lots of buffering, you don't want to be at lots of buffering. I think we know that very well. Do you want to be at no buffering? You don't want to be over there also. So you want to add some minimal amount of buffering because of high load situations. When you have high congestion, you really need some buffering. I mean, this is very fundamental, that's true, but how much amount of buffering is going to be the interesting question going forward. Basically, the problem is when you have high load, high deflection rate hurts. And you get high deflection rates when you have high load. And the idea of minimal buffer deflection router is to add a side buffer to hold only flits that would have been deflected. I'm going to give you an example. There are also other issues that happen because of too much deflection. Like when you actually have stuff circling around the network, you really want to suck them out quickly. Meaning that whenever a request, a flit arrives at the destination, you don't want to deflect that because of whatever reason. If two flits arrive at the destination at the same time, for example, and that's the same destination, if you have only one ejection port, you would deflect one of them. Not a good idea. Have just one more ejection port that's worthwhile, so that you can suck the flits out of the network very quickly, so that you don't cause deflections in the network. Because it's very costly for that flit to get deflected, because if it gets deflected, it's going to go around and come back at some point. Maybe it'll get deflected even more. If the flit is routed very close to its destination, it's at its destination, try to get it out of the network very quickly. That's the idea over here. And then it's actually not enough to have just golden packet prioritization. It's also better to have some two-level prioritization. That's the idea over here. So this leads to significant power reduction and reduced area. And also, compared to bufferless routers, it gives you better performance and closes half of the performance gap. So basically now the performance gap between buffered and bufferless, or minimally buffered, is much smaller. And we will actually see this. I think I'm going to talk about this in a little bit more. Okay, let me see. I don't know where the slides are. Where are they? Okay, I don't know what this is. So let's actually talk about this a little bit more, and then I'm going to reorder the slides, because I think this is fun. I thought I reordered the slides, but maybe this thing didn't want me to order the slides. PowerPoint has a mind of its own. Okay, we already saw this. Well, we didn't see the slide, but basically, yeah, bufferless routing is good. So the goal is to improve high load performance at low-cost deflection networks by reducing the deflection rate. How do you do that? So I'm going to give you several ideas. I've given you the high-level ideas, but let's take a look at that quickly. So I'm going to skip this one. We already talked about chipper. Now we actually want to address the performance issue. So we address the correctness issues, live lock, deadlock, which actually lead to performance problems. But now we're going to tackle the performance issue, which is performance degradations that you have at high load. If you really want a solution like this to be widely applicable, you really want to handle the high load problem. So basically, what are the key performance issues? So there's link contention that you have. There are no buffers to hold traffic, and any link contention causes a deflection. Not so good. There's also this ejection bottleneck that I mentioned. Only one flit can be ejected per router per cycle, and simultaneous arrival at the destination of multiple flits causes deflection, and this deflection is really not nice. And then there's also deflection arbitration. If you actually have fast arbitration, they deflect unnecessarily, as we will see. So we're going to have three ideas to solve the problem. Basically, to handle the link contention problem, we're going to use side buffers. So we're going to add a little bit of buffering into the router, but we're not going to put it on the critical path. Basically, the buffering is going to happen only for deflected flits. So that's a very different kind of buffering than normally you have in routers. And we're going to eject up to some number of flits per cycle. In this case, it's 2, because 2 happens to be a good number. And there's a new priority scheme that adds a little bit more into complexity into the router, like a silver level, so that you can actually prioritize some flits over others, such that you reduce the deflections. Let's take a look at these over here. So link contention, buffering a flit can avoid deflection on contention, but input buffers are expensive. We don't want to go into input buffers. Basically, we don't want to buffer all flits on every hop. That's a lot of energy. And large buffers are unnecessary because they cause high static energy in large area. So the key idea is to add a small buffer to a bufferless deflection router to buffer only flits that would have been deflected, and then make them be part of arbitration in the next cycle. So if you go back to the baseline router that we've discussed, this is a chipper router. You have injection, ejection, and then this permutation network. Okay, this somehow gets deflected because this one happens to be prioritized. It happens. Now, instead of deflecting it, we're going to put it into a side buffer. That's the idea over here. So this normally gets deflected in the baseline, but we're going to put it into a side buffer here. And the side buffer will be another level of injection. So you can see that the router complexity increases because we're injecting in from the side buffer also, and that gets prioritized over the injection port of the edge node over here. And we also need some mechanism to actually pull stuff out of the router and put it back into the side buffer. So let's take a look at what happens. This gets deflected. This goes to its destination. That's good. And instead of deflecting it, you remove up to some number of flits per cycle from the outputs. In this case, it's 1. And then that one deflected flit goes into the buffer, into that side buffer essentially. And then it takes part in arbitration in the next cycle. You reject this flit into the pipeline when a slot is available. What does that slot being available mean? When an input port is actually available. Just like the original injection policy that we have with bufferless routers. Makes sense, right? So now you realize the difference between this buffer and the buffers over here. This is a much simpler to manage buffer. There is no need for credits over here, for example. It's very local. It's completely local. Nobody else needs to know about it other than this router. Okay, and then it gets injected, hopefully in the next cycle. If it's lucky, it goes to its destination. If it gets deflected again, it may go back into the side buffer. Okay. So this could be also called the loop back buffer. Basically, you're looping back into the injection port. Okay, so you buffer some flits and deflect other flits at a per flit level. Relative to bufferless routers, deflection rate reduces significantly. There's no need to deflect all contingent flits. So if you look at a 4-flit buffer, it reduces the deflection rate by 39%. So it's significant. And you can look at the deflection rate analysis in the paper. Relative to buffered routers, the buffer is much more efficiently used because you don't need to buffer all flits. You're buffering only when it's necessary to buffer. So you get similar performance with a fraction of the buffer space and a lot less complexity because managing this buffer is easy. It's local, completely local. So let's take a look at the ejection bottleneck. I've already given you the idea over here. But basically, flits deflect unnecessarily because only one flit can be ejected per router per cycle. It turns out in 20% of all ejections, more than 2 flits could have been ejected. All but one flit must deflect and try again. And these deflected flits go around the network and cause additional contention, even though they just arrived at the destination. So actually, if you reduce the ejection width, increase the ejection width to 2 flits per cycle, you can reduce the deflection rate significantly. And you can see the analysis in the paper. So the key idea is to reduce deflections due to the single flit ejection port by allowing 2 flits to eject per cycle. So this is single flit ejection. You have an ejection over here, and you're limited. even though this came to its destination, this poor guy now gets deflected. If you have a side buffer, it gets into the side buffer. That's the good part. These things interact nicely. But now it'll get ejected later at some point. But if you have 2 ejection ports, you can eject them quickly. That's the idea. Okay, so of course the question is, what if you have this in the baseline buffered routers, right? If you have this dual with ejection in the baseline, what does it help? Actually, it doesn't help much. There's no reason to have this 2 with ejection buffered routers, because buffered routers don't run into this problem because they don't deflect, right? They buffer things. As a result, the help that you get from this is much higher in a bufferless network or in a deflection-based network. Okay, the last one is improving deflection arbitration. Basically, sometimes you incur unnecessary deflections because you use simple priority schemes in the router, and the router may not be making the right decision. So you can have age-based priorities. That's good. You get full priority order. It leads to the fewest deflections, actually. But it requires slow arbiters, as we've seen before. So if you actually use golden stage and 2-stage permutation network, like we've discussed, it's fast. It ensures forward progress. But it basically does this. It prioritizes one packet globally to ensure forward progress, but arbitrates among other flits randomly. Random is good for fast critical path. But random common case leads to uncoordinated arbitration. Now, what does this mean? Basically, okay, we've discussed this already, but basically you pick a winning flit. If it's golden, you pick the golden one. Otherwise, you pick a random one. And that random one is not necessarily good choice. And then you steer the winning flit to its desired output and deflect the other flit. So highest priority flit always routes to destination. So because each block makes decision independently, you get a distributed decision. So which means that these are not coordinated with each other. If you prioritize one flit randomly over here, that doesn't mean that you're going to prioritize it randomly over here. And that is not nice. Because you prioritize it, hopefully it's getting close to its destination port, productive port. But this router makes the decision, oh, I'm not going to pick that randomly. I'm going to pick someone else. So your deflection rate can increase significantly. So you really need coordination, which means that you need to have some level of priority when you go into the router. Okay. So that's the idea. I already said this. Like, no flit is golden. Assume that. All flits have equal priority because of that. So a red flit wins at first stage over here. It's trying to go to its destination. This one loses. Green flit loses at the first stage. It must be deflected now. So you know actually this one has lost. It's really being deflected. And it doesn't matter. Ignore the blue and yellow ones for now. So you basically get an unnecessary deflection because even though red one was prioritized over here and it was routed towards its destination, it got deprioritized over here because the decision was random and local to this 2-input arbiter. So basically both of these get deflected and the red one's deflection was unnecessary, really. Okay, so we're going to fix this problem by being more coordinated. So the idea is very simple. You add another priority level and prioritize one flit to ensure at least one flit is not deflected in each cycle. Right? You could actually expand this to bronze flit and you can do that more, right? You could add a little bit more priority into the system. So okay, highest priority, one golden packet in the network. We've discussed this, it ensures correctness. The next highest priority is one flit silver flit per router per cycle. So it's a very local priority. It's chosen pseudo-randomly and local to one router, and it enhances performance. So basically, we randomly pick a silver flit. So if you look at the flits over here, they all have equal priority. None of them is golden. And at the beginning, you randomly pick the red flit as silver. And red flit wins at first stage. That's good. Green flit is deflected at the first stage. Now red flit it wins at the second stage also, so it doesn't get deflected. That's the idea over here. So you basically consistently prioritize the red flit within the router, as opposed to doing uncoordinated decisions across the switches of the permutation network. Now, if you look at this is within a router, right? You can say, okay, I can expand this to the larger network, and you're right. So the same thing happens across routers in a network. If the routers in a network are not coordinated, you could have these decisions. You may prioritize one flit, and then the next router may deprioritize that. As a result, it gets prioritized here, it gets deflected here, it gets prioritized, deflected, so it's not a good choice in general. In general, it's good to have some coordination in the network. We didn't have that here, but some other work that we may get to talks about coordinating the routers. So that's one thing to keep in mind when you're designing networks. If you're making local decisions, that's not necessarily good for global thing. And this is one perfect example. Because if you look at a router, it looks like a network also. It's essentially doing, the network at the higher level looks like a combination of these, and you may want to do the same thing at the higher level also. This is especially true when you're looking at applications. Let's say you have packets from multiple applications. You prioritized them in one router, prioritize application A in one router. You want to keep prioritizing application A in all of the routers such that its packets get delivered, right? You don't want to increase interference in the system. So coordinating across the routers is actually useful to ensure that applications satisfy their requirements also, not just at the packet level. Okay, so I digressed a little bit, but this is an example of coordination across switches, across routers. You don't want to have fully local decisions. You don't want to have also fully global decisions because that's hard to coordinate. You really want to have some coordinated decisions. Okay, so now you have a coordinated decision. We fixed the link contention problem by using a side buffer. We fixed the ejection bottleneck problem by using dual with ejection. And we fixed the unnecessary deflection problem using two-level priority scheme. It's really the silver priority scheme. You could actually expand it as we discussed. All of these came at the cost of a little bit more complexity. Now we added some buffers, but it's not the same type of buffers. We added some more ejection ports, and we added some more prioritization mechanisms. So it comes at a cost, but performance comes at a cost. The question is, how much cost are you going to pay and how much benefit you're going to get, right? So let's take a look at the results. This is, again, some workloads. You can read the paper for more detail. And these are some of the different routers that we examined. Some of them are large buffered, typical buffered, and smallest deadlock-free router. We actually sweeped a lot of buffer sizes here. And bufferless deflection router is cheaper. And we also compared some other prior work that proposed what is it called? Adaptive flow control. It was published in 2010. It basically, the idea is you have input buffers as well as deflection routing logic. And they basically do coarse-grained mode switching. When the network is not loaded, they move into deflection routing. When the network is loaded, they use buffers. So it's good for best of both worlds, but you need to have extra logic to handle everything, meaning that you still have buffers, input buffers. So it's not that simple. And these are some common parameters you can read in the paper. And okay. So let's take a look at the deflection rates and input performance over here. So this is weighted speed up across average across all workloads, baseline. If you add a side buffer, you actually, I'm not going to go through this in detail. You can read the paper. But basically, you reduce the deflection rate if you add a side buffer, but your performance also reduces. All mechanisms individually reduce deflections, as you can see over here. Side buffer alone is not sufficient for performance because the ejection bottleneck actually remains. And if you actually start combining these mechanisms, you get much higher reductions in deflection rate. So only 10% of the flits get deflected over here, whereas in the baseline, we had about 28% of the flits that are deflected. So overall, you get significant performance improvement over the baseline by reducing deflections by a significant amount. So that's the 5.8% performance improvement. So this is compared to a deflection router, of course, right? It's not compared to a buffered router. Okay, so these are the overall performance results. If you look at the buffered routers, they're all over here. This is average. If you look at chipper, it's over here. If you look at this adaptive flow control, it's basically bufferless and buffered combination. You switch based on the load in the network. So that's actually better than any of the bufferless ones over here, but MinBD actually gets very close to that. This minimally buffered deflection router actually gets better than some of the buffered routers over here, lightly buffered routers, let's say. And of course, the same trends remain. At high loads, it's not as good, but it's not as bad also. At high loads, chipper is very bad, as you can see over here. It loses significant performance, but MinBD is much better. Okay, let's see if this is going to move. Okay, so basically that's the performance improvement over chipper. And it gets within 2.7% of the buffered router, which is not bad. So it basically closes the gap between bufferless and buffered routers. Okay, let's, yeah, this is what I was trying to get to. This is the breakdown, as you can see. You get, you see that this MIMBD adds some more buffering power, but it's not a lot of buffering power. And it significantly reduces the link power, as you can see, compared to chipper, because it reduces the deflections. So it's actually more power efficient compared to chipper as well. It's more power efficient compared to all of the buffered routers as well, right? And this, if you look at this buffered plus bufferless together, if you implement both, you're not power efficient. It's very similar to the buffered router, except for some cases where you can prevent the use of buffers. Okay. So you can see that the buffer power is very low over here. But as you keep adding buffers, our buffer power increases, of course. Right. Okay, so let's see. There's more analysis you can read in the paper. So dynamic power increases with deflection routing, of course, right? That's another way of looking at these power results, dynamic versus static. Clearly, deflection routing increases the dynamic power, but dynamic power reduces when you actually add the side buffer and reduce the deflection rates. I'm trying to get to one slide. Okay, this is a slide that's the really interesting, I think. Basically, this looks at network power on the x-axis and performance on the y-axis, and looks at the buffering space. So these are different buffered routers. The paper may have a better view of this. This is chipper, the green one over here. This is AFC. And ideally, you would like to be in the Pareto curve over here, right? And MIMBD is actually over here, which is good. So its network power is low and its performance is high. If you want more higher performance, essentially, you need to pay more. You need to pay more network power. So this may be a good Pareto optimal operating space, but for relatively little performance improvement. I'm going to go here because this is not working really well right now. Okay, so basically if you want to look at the most energy efficient network, it turns out this minimal buffering leads to the most energy efficient router design. So let's take a look at die area and critical path very quickly also. This is die area. So MIMBD doesn't add much compared to chipper. Very little area increase over chipper, and you still reduce the area significantly compared to buffered networks as expected, right? So the trade-off is you add just a little bit of buffering to get much higher performance, but this doesn't affect your area savings significantly because your buffer is really small and you don't have all of the logic associated with managing those non-local buffers. Okay. And that's 36% compared to this sort of buffering. If you want to really over-provision your buffers, actually you get a lot more. And this is the normalized critical path. So the critical path of MIMBD is actually slightly higher than chipper. I think it can be optimized even better. Maybe we didn't optimize it really well. It's 7%. So it's within the optimization range, basically. Okay. Okay, so I think I've already given a lot of the conclusions over here. And this is actually interesting because this pushes the bufferless networks toward buffering a little bit. And I think this is really the right way to go. Then the key question is now how do you close the gap between this one and buffered networks? And that's where you need to handle the congestion really well. And that's what we should talk about probably after we take a break for 10 minutes. Sound good? Let's be back at 35. I think I'm going to finish the bufferless routing path very soon. But I think this is a very good exercise actually to see the trade-offs in an example space. Even the buffering choice affects a lot of things, as you can see in the network. And I don't think we found the best place in the buffering space as to how to design a network. Okay. So then the next question is, how do you actually handle high load in a network? Let's assume that you have the minimally buffered deflection routing. Actually, part of the high load problem comes from congestion control. And we have not talked about it as much except for source throttling. And the next idea is essentially to apply source throttling to the networks. Now the network, usually bufferless networks actually, at some point I told you that if you have the load latency curve, you don't want to be operating at your saturation throughput. You want to actually be operating much earlier. You want to stop injecting much earlier. So controlling source throttling is really important as a result of that. So just very quickly, this is the idea of having source throttling in a network. And how do you do the source throttling is important, of course. It turns out, again, if you look at a lot of works, they don't care about applications. But you do want to care about applications when you're running real applications. It turns out you want to make source throttling more application aware, basically. And that's the idea in this work. I'm going to very quickly go over it in one slide. As you know very well by now, some applications are more sensitive to network latency than others. It's very similar to memory latency, right? Some applications are latency sensitive in general. Some applications are more bandwidth sensitive. Some applications are not sensitive at all. So this means that if you really want to throttle the load injected into the network, you don't want to be insensitive to the application sensitivities. Meaning that applications should be throttled differently to achieve peak performance and energy efficiency in a network. You basically want to prioritize those applications that are more latency sensitive. You want to reduce the priority of the applications that are less sensitive. And this paper proposes a mechanism to do that in an intelligent way. The idea is to have application-aware source throttling, but do it in a heterogeneous manner by respecting the different characteristics of different applications. And how do you, of course, this has all the issues that we discussed with source throttling before. Remember, source throttling had issues: whom to throttle, when to throttle, by how much to throttle. Whom to throttle may be determined based on application characteristics. This paper has a mechanism for that. I'm not going to go into detail. When to throttle is determined based on how much load is injected in the network. You can, for example, look at the deflection rates in a region and throttle that region. And by how much to throttle is always difficult. By how much to throttle is actually one of the most difficult decisions. How much do you stop injecting a node, stop a node from injecting into the network? How long? How many packets? How do you do that? It's always a lot of thresholds, as we've discussed when we discussed fairness via source throttling, right? That's the idea. And this paper has some mechanisms to do that, but whenever you do source throttling, you need to solve those problems, and it's not easy. But it turns out if you do that, you can improve performance and energy efficiency significantly, and you can bridge the gap a little bit more between bufferless and buffered networks. Can you get exactly the same as buffered networks? I don't think it's going to be possible, because buffered networks fundamentally have higher bandwidth, right? Higher saturation throughput. So by throttling it, you're reducing the inefficiencies that you cause because of deflections, but you're not fundamentally increasing your saturation throughput, right? Throttling just ensures that you're operating at a nice point such that you don't oversubscribe your network. It doesn't fundamentally increase your saturation throughput. Make sense? And that's one idea. Again, I don't go into detail. If you're interested, you can read this paper in more detail. So there's a lot to be talked about bufferless networks, actually. We didn't even talk about application of this to different topologies, but deflection routing is a very general idea. It's actually a very good idea in rings, for example. If you have hierarchical rings that we discussed yesterday, it makes a lot of sense to do deflection routing in rings, especially if you have small rings and hierarchy of small rings. Deflection doesn't cost that much. You basically circle around the small ring again, and then hopefully you get to your destination ring. Hopefully the next time you try, you're not deflected, right? So rings have less links. In that sense, there's a downside, but they also have less cost in deflection as well. And also it's very low cost. So if you want low cost, having hierarchical rings with deflection is a good idea. And this paper shows that if you have hierarchical rings with deflection, you can actually be much higher performance and more energy efficient than a buffered mesh design. Because as we discussed yesterday with hierarchical rings, your latencies could be much lower in a hierarchy of rings. So this is another thing that should be examined going forward. Actually, a lot of systems today are based on rings and hierarchical rings as well, and looking at buffering choice is important. Yeah, and this is another paper that goes into a lot more detail on this topic if you're interested in this. Okay, and that's an older one. Okay, so I'm not going to go through this in detail, but you can do more readings. Let's switch gears a little bit and talk about packet scheduling. We'll spend just a little bit of time on this because it's fun also. Because again, it's good to examine application decisions over here. The key question over here is, which packet do you choose for a given output port? Router again needs to prioritize between competing flits. Which input port should you prioritize? Which virtual channel, which applications packet do you prioritize? There are common strategies that have been used, as we discussed earlier, as round robin across virtual channels. It's a very simple scheduling policy, but it's clearly that's not very aware of applications. Oldest packet first, usually an approximation of it, because this requires full priorities. Or you prioritize some virtual channel over others to provide quality of service. So we want basically better policies in multi-core environment in general, because we know about applications better, right? This is actually true for large-scale networks, like data center networks also. You want to prioritize. If you want to input your application knowledge into the design of the system. But we're going to look at the multi-core example. So basically, the problem is you have different applications sharing a network on chip, very similar to they were sharing a cache and a memory controller. And which packets do you schedule first? So we're going to assume a buffered router, but it doesn't matter in the end. It's easier in a buffered router. So let's assume that you have lots of packets inside here. It's a congested network and, from different applications. The key question is which packet do you choose over there? So existing policies, if you look at them, they're not aware of applications. This is not necessarily a good policy. So if you're not aware of applications, you have two problems. One is the problem that we discussed. The decision that you make is local to a router. This router may prioritize one packet from application A. In the next router, that may get deprioritized. As a result, you have contradictory decision making between the routers. And this leads to inefficiency and performance loss. And this paper analyzes that problem. It's very interesting. It's very similar to what we discussed earlier. Within the bufferless router, you have contradictory decision making between the switches, right? So the second problem is, independently of this, your application obliviates, because you're treating all applications packets equally, and this is not necessarily a good thing. Because we know that applications are different, right? Applications are heterogeneous, and we want to have more heterogeneous policies, or application-aware global scheduling policies. So that's the idea in this paper. So I'm going to give you the basic idea. I'm not going to go into the details of it, but let's assume that this is the packet injection order at the processor. This particular core has injected a lot of packets. This particular has injected 2, and this one injected 1. And let's assume that we're going to use something similar to parallelism over batch scheduling. It's not going to be exactly the same, but batching is a good way of providing starvation freedom. So it's a fundamental principle. If you want to ensure that things make progress, you want to use batching sometimes. Okay, basically you mark these packets belonging to batches, and this paper uses time-based batching, because if you're over a network, if you want to preserve the batch, how do you actually preserve the batch? Whenever you inject, you actually put a batch number into the packets, such that all of the routers know which batch this packet belongs to. And then what we're going to do is we're going to rank the packets, applications, based on which one is more latency sensitive or bandwidth sensitive. In this case, this one's more latency sensitive, because if this little packet gets delayed behind this one, you're going to lose a lot of performance, overall system performance. So the ideas, as you can see, are very similar. In the end, you're doing scheduling, and a lot of the fundamental principles that we've discovered with memory controllers are going to be applicable to the networks also, except this is in a distributed setting, because we're going to look at a local router in this case. So basically, the router needs to schedule these applications. Let's assume you pick round robin. Round robin scheduling leads to a schedule that looks like this. If time goes from left to right, this is what happens. It's round robin across the virtual channels, as you can see. So basically, stall cycles that you get with round robin are very high. You can see the stall cycles by the last time unit, the time unit at which the last packet of a particular application is finished. So for a green application, it's 8 time units. For the red one, it's 11 time units. And the average is very high. If you do it age-based, let's assume the numbers over here designate age. Then you get, again, an application unaware policy. In this case, it happens to be better, but not much better. Now, if you are more application aware, if you rank the applications such that the latency sensitive ones are ranked higher, you first schedule packets from them, and then the second ranked, and then the third ranked application. And as a result, you get much better average stall cycles, average service. You can think of this as average service time across application of the different applications. So this is very similar to what we discussed earlier, right? Latency sensitive applications are prioritized. It has similarities to, and the principle of ranking we used from parallelism over batch scheduling. And also prioritizing latency sensitive applications, we used that in many contexts, certainly thread cluster memory scheduling. So again, this is a scheduling problem, and similar solutions are applicable. Then the question is, of course, how do you do the batching? But I'm not going to go into that. The paper has more detail. Okay, so if you're interested, that's the paper. Take a look. So there are a lot of other ideas actually that you can develop in a network if you want to optimize performance. It turns out, this is a very interesting one, because it turns out you have a lot of slack in the service time of packets. Some packets are more critical. So if an application has a lot of memory level parallelism, let's say it sent out 5 packets out, 5 read requests somehow. Its progress is really bottlenecked by the last one that's coming from the network. And the last one may take a long time. The first one may take not so long time, which means that the first one has a lot of slack. It can be delayed until the last one comes back, approximately, right? Because there's some progress that it can enable in the core. But if you think of it in an abstract manner, if the application can make progress only after all of the 5 requests come back, you're really bottlenecked by the last one that comes back, which means that you can delay all of the packets that you sent to the same time as the last one, to the same time at which the last one is going to come back. That's the idea. You somehow figure out the slack that you have in each packet, and you prioritize the packets that have less slack over others. I think this is, again, a fundamental principle. As long as you can do this in an easy way, you really want to schedule things based on slack. So slack can be based on the last packet arriving, because you're not making progress until the last one arrives, so there's a lot of slack on the other ones that are supposed to arrive earlier, or that could arrive earlier. Or it could be based on some deadline, right? We've seen this actually in accelerators. If you actually know that you don't need the packet to arrive until this point, you know that you have some slack in the servicing of that packet, and you prioritize the packet that has the least slack in the system. And this actually leads to significant performance, and the paper has a lot more detail, which again I'm not going to go into over here. So there are a lot of other issues in on-chip networks, or networks in general. Quality of service is one. We're not going to tackle that. We don't have time. Actually, let me see how much time we have. Yeah, we don't have that much time. But it's very interesting, especially low-cost quality of service mechanisms are really important. And there's a lot of work in the internet, but on-chip networks are lacking actually in this domain. And this is actually very interesting work that has a particular idea, which maybe I will talk about very quickly. So basically, what if you want to design an extremely large-scale network, like thousands of nodes? You want to be extremely efficient for sure, no question about that. But you want to do some other things also. And we want to provide quality of service also. This paper tackles this grand problem, if you will. You want to design a very large-scale network on chip, and you want to provide service guarantees, you want to be scalable, you want to be energy efficient, you want to be high performance. I'm not going to go through all of the details over here, but I'm going to give you the idea related to quality of service especially. So this is all you want actually from a very large-scale network. And the idea, a big novelty in this paper is, if you want to have quality of service in your network, if you want to put it in each router, it's expensive. Basically, yes, you have buffering, but now you need to have more buffering to distinguish between different quality of service classes. You need to do arbitration, depending on what kind of quality of service you want to provide. You need to do bookkeeping for each flow in the network, even though it may not be occupying buffers at that point in time. So there's a lot of overhead to provide quality of service to different flows or different applications in the network. And actually, there's one proposal that we had that makes it much more cost effective, but it's still expensive actually. So the goal is to provide quality of service guarantees at low area and power cost, because having it across 10,000 routers and every router enforcing those quality of service guarantees is not simple. So the idea in this work is to have isolation. Basically, create a region in the network where the shared resources are isolated, and you support quality of service only within that area. Everything else is quality of service free. And design the topology so that applications can access the region without interference. That's the interesting part. Now we're going to modify the topology such that we support this quality of service aware region. So if you look at a baseline quality of service enabled chip multiprocessor, it looks like this. Quality of service is everywhere. in the routers. And this example actually shows concentration also. Basically, you have 4 nodes connected to a router, and you have 4 by 4 of these 4 nodes, as you can see. And you can see that these are shared resources over here, and these are private resources. And you have quality of service enabled routers everywhere. And you may have a mapping of virtual machines look like this. Virtual machine may be mapped to these cores, for example, number 1. Virtual machine number 2 may be mapped to these cores. Virtual machine number 3 may be mapped to these cores. Yeah, okay, I guess I've already said that. So in this case, there are some downsides. The contention scenarios are whenever you want to access shared resources, you have memory accesses, you have contention. You may have intra-virtual machine traffic. You may have inter-virtual machine traffic that leads to essentially contention. So whenever you want to access a shared resource, for example, and this other virtual machine wants to access that shared resource, you have contention over here. So that's why you need to provide quality of service in the routers that are over here. So we don't want to do that actually. We want to provide network-wide guarantees without network-wide quality of service support. So the idea with Kilo and Oka is this. We have a lot of network connectivity on chip. And we can use that naturally to reduce interference among flows. And by doing that, we will limit the extent of hardware quality of service support in the routers. Basically, we're going to use a topology as an enabler for reducing the quality of service support, as a result improving the efficiency. So this requires a low diameter topology. That's why low diameter is good actually in general. And we had some other work in the past called multi-drop express channels. It's a low diameter topology. It's actually a very simple idea. It basically says you have a link over here. You have treat it as a multi-drop bus. So this is really a bus that has drops in each of these nodes over here. And we're going to take advantage of that multi-drop bus. And it turns out this is, of course it's a trade-off. This doesn't buy you the highest performance. This doesn't always buy you the highest efficiency, but it gives you very high scalability and very high efficiency in general without getting you to the highest performance in all traffic patterns. So it's not good for all traffic patterns, but it's actually a good topology if you want to achieve low diameter. So the idea over here is we're going to use that topology to reach these dedicated quality of service enabled regions. So we're going to designate some part of the chip as quality of service enabled. Rest of the die is quality of service free. And then we're going to map our virtual machines or whatever applications. And you can see that the cost has reduced significantly to begin with. Now, how do you actually ensure that this virtual machine has non-interfered access to this quality of service area, if you will? We basically provide traffic isolation using a low diameter topology. And the topology in this case is a multi-drop express channels, but you can actually have some other things. So this way, this region can access, so this virtual machine can access this region with its own link, and this virtual machine can access its own region, this region with its own link. And they do not interfere with each other. So that's the advantage of having a topology that looks like this. It's low diameter. This can access directly this region. And this region can also access directly. This region can also access directly. As you can see, they have separate links. And these links don't interfere with each other. Okay, and if you want to actually communicate between this virtual machine and this virtual machine, unfortunately, we're not going to be able to do that anymore because you would contend with this virtual machine. So we're going to disallow that sort of communication. We're going to force that communication to go through the quality of service of our region. So that's the cost that you pay. You basically don't want to interfere with this one. As a result, you go through the quality of service of a region to communicate with other parts of your virtual machine or with the application. Right? So that's the idea basically. The quality of service of a region is limited. You use topology to reach that quality of service region, every region in an isolated manner across different applications. And you ensure that applications do not interfere with each other in the non-quality of service region. And there's a lot more other optimization that's done over here. Basically, there's optimized flow control that reduces the buffer requirements in the quality of service free regions. You should take a look at that. There's a lot of work in optimizing buffering resources, and this work takes it to the next step. Let's take a look at the results very quickly. So if you actually do all of this, This is a baseline network. It's very optimized actually. This multi-drop express channels plus this preemptive virtual clock quality of service mechanism that we had developed. Basically, router area is huge, as you can see. If you use what we've discussed, you actually reduce the router area, overall area, network area significantly. Even with buffered networks. We're not eliminating buffering here. We still have buffers. And buffers actually still consume a lot of the area, as you can, well, it's not obvious in this figure. But the quality of service aware region actually occupies the screen part. So there's a lot of area that's dedicated to quality of service aware region in this case. Energy comparison, energy is actually pretty good compared to the baseline again. It's not as good as this other one over here, but that other one also has high area. That other one you can, so this has elastic buffering and also quality of service aware regions. And there's more work, more examples over here that I'm not going to go into since we don't have time. So basically this is an example of the complexity of network. I've glossed over a lot of detail over here, but basically you want to provide quality of service, you want to minimize area as much as possible, maximize scalability, minimize buffering, maximize energy efficiency. And this one example of a network design that does that, and there are several ideas. And it does provide strong guarantees in terms of quality of service in this case. Okay, and this is not what I'm going to talk about, but you can have the slides for your own. This basically talks about how to make low diameter topologies. And I think low diameter topologies are very good in general for latency. So it's good to look at low diameter at low cost going forward. Any questions? No questions? Okay, so next week we have an exam. I hope you'll prepare. I would suggest doing the homework because homework is actually good for the exam in general. Yes?
Just to clarify, it's on Thursday, not Wednesday, right?
Yes, exam is Thursday. Wait, 20th, yeah, it's the last day of classes basically. Last day of our class. I don't know if it's the last day of classes. Yeah, it's on Thursday. On Wednesday, what should we do on Wednesday? Should we have a review session? Should we have fun? Should we have another lecture? You won't be responsible if there's another lecture. Any thoughts?
Review?
You would like the review? Yes, for sure? Okay. Yeah, then we'll have a review session on Wednesday. Sound good? Okay. Any burning questions before we part? And by the way, the exam will be more focused on the second half of the course. Let me put it that way. Technically, it's the entire course, but we're not going to. I mean, there might be some basic knowledge that you need from the entire course, of course, but you can expect most of the questions to be from the second part. Okay, I guess I'll see you next week. Have a good weekend.